Initial mean. No, look. The mean of xt. Well, yeah. Let's use my notation. Okay, so the optimal estimator is just that. If your observations are white but completely uncorrelated with what you care about. You know, because remember we assume that all these guys are mutually uncorrelated. So if that's gone, this is uncorrelated with everything up here. And so the best predictor is just the mean. And we can work out the mean because I can take the expectation of both sides, and the mean evolves according to a simple linear equation. And what it is there, so you can see how the mean evolves. So the common filter isn't completely worthless, but you could have figured this out pretty quickly, right? You could have taken the mean of both sides here and been done with it. The next point is, typically everything's constant. No, that's not true. Typically we assume the model is time invariant. So we assume that this is independent of time, this is independent of time, F doesn't depend on time, H doesn't depend on time. And then under conditions, and this guy is well behaved. So if you look at that F minus KH, and you take its eigenvalues, they're all less than 1. You know, and that's what I mean by this being stable. And that's when it doesn't matter, because if you don't really know the mean, the impact of the unknown mean will decay geometrically quickly. So you can just pretend it's 0, just ignore it. But it's not always true. I mean, there are cases where it doesn't work.
Your system has to be stable.
No, it's more than that. It's not stable, it's stability. So take a control course. It's much harder than that. It's much easier than that. The answer is very, very deep and long. You need detectability, okay? It's not stability, it's detectability. So it's observability is enough. But detectability is what you need. It's just, all right. If you know, I mean, really. What else? There's another wonderful fact, is that sometimes, so I'm not giving you a formula for this right now because it would take the remaining time to write it down. But sometimes this is actually not given to you in advance. It's really hard to explain this, but I mean, it may be that you're estimating parameters in your airplane as you're going along, you know. I mean, my PhD thesis, half of it was about this, about I've got parameters in a system, and I want to control it as I estimate. So these things are basically, it's like there's two measurements. There's a measurement here of y, and there's also system measurements that you take on the fly, and you take those system measurements and maybe estimates of the covariance as well, and you take those and you plug those in to get your KT. So then all the stationary business goes out the window, and then it's a really dangerous, to answer your question. I mean, it really is not easy at all. So it's not, what's that? It's really not hard. I make a big deal about this. It's just, the derivation of the Kalman filter, figuring out what this, there's two things you need to do, right? You need to figure out why is that the innovation sequence, and you have to figure out what the hell is that gain. And you know where this is coming from. I mean, I made such a big deal about W and Z, and so here is my estimate given Z, and there's my estimate given W, sort of. I mean, just exactly following what we talked about before. But we've got to figure out how to put this in the context of 15 minutes ago. So let's do that. Let's start that. I knew I wouldn't do it. Let's start that. I won't get into the meat of it. Oh, it's right there, yeah. Cool. I can't believe I didn't think of putting this together. We've got to link up that and that. All right, so this and this. Those guys are the same thing. So you got to figure out what is Z and what is W. And you guys know what Z is, I'll bet. It looks like Z is its innovations. And then W, we have to go and work on that. So I'm going to give you the action plan, and then we'll quit for the weekend. Although I hate it. I wish we could just do it. It would take us 10 minutes. So we don't have 10 minutes. So I have my previous estimate and I have YK. What am I going to get from that? I'm going to go find my estimate of XK. All right. So basically, Hayek calls that the information update. And that uses this thing here. As I get more information, how do I update an estimate? So that's my capital Z over there. Right? And then you have the dynamics. And so this part here, basically just got to apply that business over there. And this part here, why don't we just do it? I mean, geez. Where's our system equation? This is easy. One line. Somebody tell me how to do it. I've got an equation there, I plug it in, right? All right, and this wide sense expectation operator is linear. So if I got an expectation of a sum, it's the sum of the expectations, right? And this guy is assumed to be orthogonal to everything else, right? So this guy's orthogonal to all the VKs and to the X0 and everything. So the estimate of WK given all the YKs is 0. So you just plug that in, and that's just the definition. Again, the FKs seem to be deterministic. It's just a matrix. It comes outside. So talk about easy. It's a one-liner. All right. And so this takes a bit of work, and not much work because it's right there. The tricky part then is that when you go through this, you get this business here. We know that this conditional mean, which is what comes up over here, involves an inverse covariance matrix and all this stuff, and that turns out to be a monster. All right, so that's why if you do the whole common filter, you need a 2-hour lecture. But I'm going to give you just the main ideas and then send you to Wikipedia, Bruce Hayek's book. Not now, but we'll just spend a half an hour in the next lecture and derive the common filter. And just, so so take a picture of that. We'll need that back on the blackboard next lecture, and then we'll nail it. All right, so I know you're all nervous about getting your quizzes back, so I've got that in the homework. The homework I'll just pass around, I guess.